Good afternoon. Please note before we begin that I made these notes prior to presenting the beginning of 2.2 in class yesterday. So if I repeat anything from yesterday, feel free to fast forward through the video. In addition, if I move too fast at any point in time, also feel free to rewind or pause the video. Alright, so let's go ahead and begin. We left off essentially talking about the derivative and all of the shorthand derivative rules. Now we're going to show how to apply them to various problems. Starting with exercise 50. In exercise 50, we want to find all of the points on the graph of f of x equals 12x minus x cubed where the tangent line is horizontal. So to tackle this, we really need to think about what they're really asking us, and we have to relate it back to calculus, in other words, derivatives. So we want to know where a graph is horizontal. So what does this mean? Well, yes, it's a flat line, but remember we're trying to think about derivatives, and derivatives represent the slope of the tangent. So if we want a horizontal line, we're looking for where the slope is 0. Something very important that you need to note is the relationship between f of x and f prime of x. The derivative value will always be equal to the slope of the tangent of the original function f. So if we want the tangent slope to be 0, we want the derivative value to be 0. This is a very important relationship that I will stress throughout the rest of these notes as well as the rest of the year. So since we're looking for a tangent with a slope of 0, we're looking for where the derivative is equal to 0. So let's go ahead and begin by finding the derivative. We start with our function f of x equals 12x minus x cubed. To take the derivative, we're going to use all of those shorthand rules that we learned yesterday. The derivative of a constant times x will just be the constant, so we'll get 12 out of this first term. And the derivative of x cubed will be 3x squared. We drop the power down and subtract it by 1. So there's our derivative, 12 minus 3x squared. Because we're looking for where the derivative is equal to 0, all we have to do is set it equal to 0. Once we've set our derivative equal to 0, we go ahead and just solve algebraically. So I can add 3x to the other side, divide by 3, and then take the square root. Remember, when you take the square root of an equation, you have two solutions, both positive and negative. So our two solutions are plus or minus 2. Now, you may be quick to just say this is our answer, but go back and read the question. The question was, find the points on the graph of f of x equals 12x minus x cubed where the tangent line is horizontal. Note, find the points. Right now, all we have are x coordinates. If we would like the points, we have to go back and plug these x coordinates into our original function to find their y values. Note, we're plugging it into the original function to find the point, because if we plug it into the derivative, we're just going to get 0, the slope of each of those points. If we plug into our original function, we get 16. And if we plug in our negative 2, we'll get negative 16 out of f of x. These are our solutions, 2, 16, and negative 2, comma, negative 16. The next thing we're going to talk about is the graphs of f of x and f prime of x. Keep in mind that f prime is calculating the slopes of the tangents. So, if f prime is negative, then the tangent has a negative slope. Another way to describe this is when f is decreasing. Likewise, if f prime is positive, then the tangent line has a positive slope in f, and f is increasing. Next, we're going to apply these to matching graphs of f and f prime of x. Let's go ahead and take a look at exercise 66 from your book on page 141. I'm going to go ahead and put the graphs up on the board, but feel free to look at a textbook if you want to go back and forth between each of the graphs on your own. So you'll notice that the graphs on the left in blue are all of your f of x functions, and the graphs in pink are your f prime functions. In the directions, we are to match the f of x with its appropriate f prime. In order to do this, we really need to remember the relationship that I noted in example 50. The slopes of the tangents of f are equal to the values of f prime. I'll say it again. The slopes of f are equal to the values of f prime, because that's what we're going to compare. The slopes of f to the values of f prime. So let's go ahead and do that. I'm just going to start to analyze graph A. And I'm looking at the slopes because remember, f, we want to compare the slopes. So what would you say the slope is right at the beginning? I personally would say that's a 0. It's a flat line. So I'm going to go ahead and mark it with 0. And you can note it at the bottom of your notes if you're sketching this graph, if you'd like as well. Now, what type of slope do we have here? It looks like we have a slightly positive, although it is positive. So let's go ahead and mark that positive. Okay, so positive, and it's continuing to be positive. And it's continuing to be positive. Looks like all the way up until our peak here, where it achieves a 0. So it's positive all throughout. We also then, after that peak, we have a negative slope because the graph starts to go down. So let's go ahead and mark that as negatives. And then we are negative all the way until we reach the value right here, which again would have a slope of 0. After that, we again have a positive. Sorry, I'm having issues grabbing these plus signs. And then our peak here is again another 0. And then down we have another negative. So what we're looking for is essentially a f prime whose values go 0, positive, 0, negative, 0, positive, 0, negative, because that's what our slopes do in f. So let's take a look at f prime. This one does look like it sort of starts 0 and goes positive, and then it should peak, or I'm sorry, the values though should be 0 right here, where this one sort of gets even more positive. So I would say this graph does not go positive, negative, positive, negative. It looks like this value graph goes positive, 0, negative, and that's all. So I'd say that one's out. Let's take a look at the next one. The next one's values start off positive. So it's definitely not starting off at 0 where we would want. In this case, the values would go positive, negative, positive values. So that doesn't match up with our graph in A. Let's take a look at our last graph 3. This one does start off 0, goes positive, 0 again, negative, 0, positive values, 0, and then negative. So this one does have the pattern that we're looking for. 0 slope, positive, 0 slope, negative slope, 0, positive, 0, negative. And if we again compare that to the values, it looks the same. So it looks like A goes with graph 3. Let's take a look at B. If we look at the slopes of the tangent, it looks like our slope is maybe starting off at 0. We're not quite sure, but it definitely has some positive slopes afterwards. So there's some positive slopes here. And we have a 0 slope achieved here at the peak. And again, remember, we're thinking about the slopes, and then it goes negative. Now if we look at our derivative graphs and look at the values, we see that the very first graph has positive values, values above the x-axis, all the way to the middle, where it has a 0 value, and then negative values all the way to the end. So number 1 looks like it goes positive, 0, negative, just like the slopes of our graph in B. So 1 matches with B. This leaves C with 2, but let's go ahead and convince ourselves the slopes of the tangents of F are positive all the way till about here. And then right here we have a slope of 0, slightly negative, 0, and then positive again. So it looks like it's positive, a little bit negative, and then positive again. And if you look at our graph C, we see positive values, values above the x-axis, 0, a little bit negative for a short period of time, 0, and then positive again. And that's why our last graph is indeed C. Next, let's talk about the derivative of e to the x. So, what is the derivative of e to the x? Because this is not a power rule, we can't use any of our shortcut methods to derive this derivative. So, the only thing we have is the definition of the derivative, and that's what we go back to. Let's go ahead and prove the derivative of e to the x. So once again, as I just mentioned, we're going to go back to the definition of the derivative. And I like to use the second definition because it doesn't have, it doesn't have an x already in it. So when we plug in x for our a values, we won't have any confusion. All right, so let's go ahead and start. F of x plus h. If our function is e to the x, that would be e to the x plus h minus the function itself, so e to the x all over h. So there's the definition of our derivative for e to the x. Now we're going to use our exponent rules to separate e to the x plus h into e to the x times e to the h. And this is just an exponent rule. No fancy math here. Now if you look at your numerator, you can see that e to the x is repeated in both terms. So we could actually factor it out. And we have the limit as h approaches 0 of e to the x times the quantity e to the h minus 1, all over h. Using your limit properties, you can actually separate this into two separate limits, the limit of e to the x and the limit of e to the h minus 1 all over h. After separating, we can look at the limit as h approaches 0 of e to the x. Keep in mind that when you write this limit, h is our variable. X is treated like a constant. So if we're just plugging in 0 for h and there is no h left, then the answer is just simply e to the x for the first part. For the second part, we have to do a little bit more work and we'd have to create a table of values. Let me convince you without actually doing it with you that if you use a table of values for this particular limit, you'll find that the limit is 1. So this means that our limit is going to be e to the x times 1, or e to the x. Therefore, the derivative of e to the x is e to the x, and you can go ahead and fill that in. This is the easiest derivative you will come across. Let's take a look at an example applying the derivative of e to the x. Here we're going to find the tangent line to f of x equals 3e to the x minus 5x squared at x equals 2. Once again, tangent lines are very important. You should be able to write a tangent line at any point throughout the year. What two things do you need to write the equation of a line? A slope and a point. So we need to find both of them. Let's start with the point. To find the point, we need to find the y-coordinate because we already know the x-coordinate. To find the y-coordinate of a point, you need to plug it into the original function. So we find f of 2, which is 3e to the second minus 20. This means that our point is 2, 3e to the second minus 20. Next, we have to find our slope. To find our slope, we want the derivative function, because remember, the derivative is the slope of a function. So the derivative of 3e to the x is just simply 3e to the x. And then our derivative of 5x squared becomes 10x. This makes our derivative function 3e to the x minus 10x. We want the slope specifically at the x value too. So we're looking for f prime of 2. So we just simply plug in 2 into our derivative, and voila, we have our slope value. And I know this may seem like it's not an actual value, but it is, because remember, e is a constant, so this is actually one giant number, 3e squared minus 20. So now we have our slope, 3e squared minus 20, and we have our point, 2, 3e squared minus 20. So we go ahead and write our equation of our tangent. Remember that the equation of a line is y minus y1 equals m times x minus x1. And we plug in our values. Y minus our y value equals the slope times x minus 2. Because our directions just said to find the equation of a tangent, we're actually done. If you feel the need to simplify, you can, but it's not going to get too much better with this x running around on the right-hand side. So that's our final answer. The last thing I want to talk about are examples of functions that are not differentiable. Just like when we were talking about continuity and had examples of discontinuous functions, we also have examples of functions that are not differentiable. Here are the 4 examples of non-differentiable functions. The first is a corner. An example of this would be your absolute value of x graph. A corner is simply a graph which approaches one slope on the left and a completely different slope on the right. So as you can see on the absolute value of x, we have a slope of -1 on the left and a slope of +1 on the right. It's essentially any sharp turn that you make. Now this is a pretty abrupt turn, but you could even have a slope of 1 going to a slope of 1.2 immediately, which would be considered a corner as well. The second example is a cusp. A cusp is essentially when a graph essentially reaches a peak, just like a cusp would. Technically, right at that corner, there is no slope or there is no derivative value because it would be completely vertical. This leads me to the next example, a vertical tangent. The graph, the cube root of x does not have a derivative at 0 because technically the slope is directly up and down or vertical, and there is no slope for a vertical line, and thus no derivative value. So we say that this graph is not differentiable at 0. Last but not least, any type of discontinuity is not differentiable. So in this picture, they gave you a jump discontinuity. However, any type of discontinuity is also not differentiable. So a removable discontinuity is not differentiable, an infinite discontinuity is not differentiable, and neither is an oscillating discontinuity. All of those are not differentiable. Since any type of discontinuity would result in a function that is not continuous, we actually have our last theorem and last part of the notes for the day. If a function is differentiable, then the function must be continuous. This is important because oftentimes in problems, it will state that the function is differentiable. And if the function is differentiable, you can assume that the function is continuous. This is kind of like the idea of a square and a rectangle. All squares are rectangles, but not all rectangles are squares. All differentiable functions are continuous, but not all continuous functions are differentiable. Case in point, the absolute value of x. With the same regards, if I tell you a function is not continuous, you automatically know that it's not differentiable. This is a very important thing to note. And that's the end of the notes.